In the mid-1930s, Enrico Fermi attempted to synthesize a new element. And he did this by bombarding uranium with neutrons. The idea was that if you could get a neutron to kind of stick, to get incorporated into the nucleus, that it might undergo beta decay, converting a neutron into a proton, and then you would have a different element. So this is the reaction. Uranium-238, throw a neutron at it, get it to stick. This will give you 238-239 uranium, which would then undergo beta decay, producing a new element, which of course we know what that element is now. Where'd you go? It's neptunium, but that was not, had not been discovered yet. So he did detect beta emission, but he never did examine the products chemically to see if a new element had been formed. That's always been, I keep meaning to look into that. Why didn't he do that? It seemed like kind of an obvious thing, but he didn't. So as often happens, other scientists repeated his experiments, Meitner, Strassman, and Hahn, and they did study the products, and they found that the products contained several elements that were lighter than uranium. Fermi was predicting something heavier than uranium. So this was a discovery that changed the world forever. 1939, January 6th, this group of scientists reported that neutron bombardment of uranium resulted in nuclear fission, the splitting of the uranium atom. This was previously believed to be completely impossible. So this was a very, very big deal. You can take an atom and you can break it into pieces. It was a crazy idea. So the uranium atom split into barium, krypton, 3 neutrons, and a whole bunch of energy, a tremendous amount of energy. So this is uranium-235, and less than 1% of uranium is uranium-235. Uranium-238, the most common isotope, does not do this, but uranium-235 does. So fission, splitting of the atom. Fission as opposed to fusion. Fusion is where you put 2 atoms together. So this led to the development of the atomic bomb. So if you have a sample that's rich in 235, it can undergo a chain reaction. So you bombard uranium-235 with a neutron, it produces krypton, barium, and 3 neutrons. Each of these neutrons, in theory, could hit another uranium-235 and cause another fission event. And each of these is generating 3 neutrons. So if they are all successful, this is going to get out of control very, very quickly. And remember, there's a tremendous amount of energy released with each of these fission events. So in order for this reaction to be self-sustaining, you have to have a certain amount of uranium-235. If it's just the normal amount, which is less than 1%, these neutrons that are produced are not going to find another uranium-235. They're going to run into uranium-238 and nothing's going to happen. So you have to have enough of the 235, you have to have enriched uranium for this to be self-sustaining. Any questions yet? So this was during World War II, and so the U.S. Scientists were very afraid that Germany would figure out how to make a bomb using this process before we did. And so U.S. scientists persuaded Albert Einstein to write a letter to the President Franklin. I'm going to read it to you because I just think it's kind of interesting. So August 2nd, 1939. Sir, Some recent work by E. Fermi and L. Szilard which has been communicated to me in manuscript, leads me to expect that the element uranium may be turned into a new and important source of energy in the immediate future. Certain aspects of the situation which has arisen seem to call for watchfulness and, if necessary, quick action on the part of the administration. I believe, therefore, that it is my duty to bring to your attention the following facts and recommendations. In the course of the last 4 months, it has been made probable, through the work of Joliet in France, as well as Fermi and Szilard in America, that it may become possible to set up a nuclear chain reaction in a large mass of uranium, by which vast amounts of power and large quantities of new radium-like elements would be generated. Now it appears almost certain that this could be achieved in the immediate future. This new phenomenon would also lead to the construction of bombs, and it is conceivable, though much less certain, that extremely powerful bombs of a new type may thus be constructed. A single bomb of this type carried by boat and exploded in a port might very well destroy the whole port together with some of the surrounding territory. However, such bombs might very well prove to be too heavy for transportation by air. So, in response, the U.S. government said, well, let's try to make an atomic bomb before the Germans do. So the Manhattan Project was launched in 1941. And a nuclear weapon, the first one, was detonated in 1945 in New Mexico. It had the force equivalent to 18,000 tons of dynamite. That's 36,000, no, not 36,000. A ton is 2,000 pounds. So 36 million pounds? Yeah, of dynamite. At this point, Germany had already surrendered, but we were still at war with Japan. And so we dropped 2 bombs on Japan, which killed 200,000 people. Since then, controlled fission reactions have been used to generate electricity. And the wonderful thing about this is you can generate electricity this way without generating any air pollution. No gases are given off, no greenhouse gases, there's just no pollution, no air pollution. So nuclear fission generates about 20% of US electricity, up to 70% of electricity in some countries. It's a very, very efficient way to make electricity. So a pencil-sized cylinder of uranium could power a typical car for 20 years. Think about all the gas that you put into a car over the course of 20 years. It's a lot. Pencil-sized, make enough energy for that. A coal-burning power plant, which a lot of electric generating plants are fueled by coal, would need 2 million kilograms of fuel to generate the same power as 50 grams of fuel in a nuclear plant. And of course, when you're burning coal, you're putting all sorts of bad things into the atmosphere because coal is not a very clean source of energy. How does nuclear power work? The fission reactions give off a lot of energy, which a lot of that is heat. So heat is generated by the fission reaction, and that's used to boil water to make steam, and the steam turns a turbine on an electric generator. The basic idea here is the same as for a coal-burning electric plant. In a coal-burning plant, you're burning coal to generate heat, to create steam, to turn a turbine and generate electricity. Here, instead of burning coal, we're using this nuclear reaction. So here we have the nuclear reactor, and we have our fuel rods, and these are the enriched uranium-235. And then between them, we have control rods that can be lowered and lifted to control the reaction. Because if you don't control the reaction, it can get out of control, and you can end up, in theory, having a detonation. So those control rods are made of a substance that absorbs neutrons. So the way to slow down this reaction is to put something in there that's going to absorb the neutrons so that they can't hit uranium and cause more reactions. Major drawbacks to nuclear power are nuclear accidents and waste disposal. Anybody have any questions about how nuclear power works? This is a very simplistic view. So the biggest problem is nuclear accidents, and of course these have happened numerous times. The fission reaction can overheat in spite of safety precautions. Chernobyl, an incident happened in Chernobyl in 1986. Just, for weird personal reference, I was in college when that happened. I know, right? How did this happen? They were doing an experiment to see if they could reduce maintenance costs. And so they disabled some safety features, and their experiment was a disastrous failure. The safety features were disabled, and so the graphite core was partly graphite. It overheated and began to burn because graphite is flammable. There were 31 immediate deaths, and a 32-kilometer radius became uninhabitable. That area is still not habitable. It was a really, really terrible accident. More recently, in Japan, Fukushima, 2011, there was a 9.0 magnitude earthquake that triggered a tsunami. So the tsunami flooded much of Japan, and the cooling ponds for the nuclear reactor got flooded. So this caused the pumps to fail. So in order, to control this, you need to have some cooling water. And so, you have these big ponds outside, and there are pumps that pump this cool water back in to help cool the reactor. Well, the pumps got plugged up with debris from the flood. This was not something anyone had anticipated. It had never happened before. So because of that, there was a partial meltdown. There was significant radiation release, but it was much, much lower than in Chernobyl, and there were no radioactivity-related deaths. So we've gotten a lot better at safety precautions here. Neither incident was a nuclear detonation because the uranium fuel in the reactor does not have enough 235 in it to produce detonation. The worst that can happen is this overheating, but you overheat it too much and then the containment system breaks down and radiation can be released. U.S. nuclear plants have lots of safety features that are designed to prevent such accidents. That doesn't mean to say that we haven't had accidents in the U.S. There was one, I think I was in elementary school, 3 Mile Island on the East Coast. There was a big problem there. Any questions? So accidents are a problem. The other problem is disposal of the waste. So we don't put any air pollution into the environment using nuclear power, but we do have the spent nuclear fuel that we need to dispose of. And of course, that is radioactive. And it's not a lot of fuel, but it's radioactive, and a lot of these products have long half-lives, so they're not going to go away anytime soon. Currently, nuclear waste is stored at the nuclear reactor. They were developing a single disposal site, but they stopped working on that in 2010. It's just been bogged down and is just kind of in limbo there.